Hi guys, so welcome to our last installment of Chemical Equilibrium, where we're going to talk about LeChatelier's principle. And we might remember this from Chem 1. This is where as we change concentrations or pressure or the amount of heat / energy going in or out of a system, we change which direction the reaction is occurring, whether it's continuing forward or it's going to reverse. So we see here LeChatelier's principle. I'll give you a second here to read that. Okay, and let's take a look. So if we change the concentration, the system is going to shift away from where we've added more substance. So let's take a non-chemical idea of this, right? So you guys know from Chem 1, my s'mores example in stoichiometry. If we have ingredients to make s'mores and we need to make 500 s'mores, okay, so that we can sell these as a fundraiser for Science Honor Society, let's say. Okay, as we have a whole lot of ingredients and no product at all, we're going to work really hard to make as much product as we possibly can, right? And as we have more product and less reactants, we're going to slow down. But if someone comes in and adds a whole bunch of reactants, brings us more ingredients for our s'mores, then we're going to speed up making more products. Okay, let's go the other direction, in that if we need to make 500 s'mores, and another teacher's class is making s'mores also, and they say, hey, we made all these extra s'mores, and they bring them over to us, all of a sudden we don't have to make as many s'mores. We don't need to make as much product. They've contributed to our product, they've added more product, and so we can slow down, and we're going to reserve some of our reactants. So the same idea here. We do need to make sure that we are looking at states of matter here, okay? So if we add more solid, that is not going to affect our equilibrium constant, right? It only matters if we add gas or to aqueous solutions, right? So I'm going to grab my tablet here. So if we add more of this guy, then we are going to force this chemical reaction towards making more product. If we add in some more product, we have more of these guys, then we're going to force our reaction back this way. But if we add more carbon, more solid, that is not going to affect our equilibrium constant. And so that means that our K, right, when we change things in LeChatelier's principle, when we change a reactant or a product, we are shifting K in a direction. And we can always use Q to check which way we are shifting that. Remember, Q is our concentration at that moment in time. And so we can always compare that to our K. Here we're looking at temperature. Temperature is depending upon whether we have an endothermic reaction or an exothermic reaction. We treat energy as a reactant or a product. So in an endothermic reaction, energy is required. So energy is a reactant. Ooh, I'm going to change my color real quick here before I write, since I have that blue background. So here we see we have positive H, right? So that means that it is going in, and it is endothermic, and so that means that it is a reactant. So we could actually, if we wanted to, we could fit it into our chemical formula here, writing nitrogen plus oxygen plus 181 kilojoules of energy would result in nitrous oxide. So We could write it that way. So if we were to take this chemical reaction and put it on a flame, we're going to force it towards product because we are adding more energy as a reactant. Whereas if we look at an exothermic reaction, here we have one. We know it's exothermic because it's negative right there. Let me turn that into an arrow. It's negative, which means that we would really write it over here as part of our products. Now notice I'm writing a plus sign there because I'm writing it on the product side. It's negative because it's exiting, so it counts as a product. So if we take this reaction and we put it on a Bunsen burner and we heat it up, we're actually going to force it the opposite direction. And this guy is going to decompose back into its reactants or ingredients and break down that product. And so we're going to have a shift to the left there because we're adding heat into there. And we can think of some real life examples where if we add heat, things decompose more quickly. In this situation, this endothermic situation, we're adding heat and we're synthesizing. These two things are going to bond together faster when they have more energy. All right. Pressure. So when we change pressure, how does that affect our system? So the overall pressure of a system is increased. The equilibrium will shift where there are less moles of gas. So if we have a whole system and we, let's actually go back. We'll use this guy. Okay, so here we have 2 moles of gas. And on this side, the reactant side, we have 3 moles of gas. So if we were to put this system under increased pressure, it would actually go toward product because we have fewer moles of gas. If we were to reduce the pressure, then it would go to where there are greater moles, which would be the reactant side. So we use those coefficients to tell us how many moles are on each side when we're talking about a gas. Addition of an inert gas, which means a gas that's not involved into the chemical reaction. So if we go back to this guy here, we have sulfur dioxide and oxygen. If we were to suddenly add carbon dioxide to this system, like let's say that these guys are in a container and we add some carbon dioxide gas, that has no effect on the equilibrium of a system because that gas is not participating in the reaction. And then our last one here, changing the volume of the system does affect pressure. We know from Boyle's law, right? Volume and pressure are indirectly related. As we increase the pressure, we're going to decrease that volume. And that goes back to this guy. So if we increase the pressure, then we're increasing the overall pressure of the system. So if we make a volume smaller, we're increasing pressure. If we make a volume bigger, we're decreasing pressure. And it goes back to what we said there in point A. So let's look at some pressure examples here. I'd like you to pause the video and give these a try. You are putting, these are in 3 separate containers, and we are increasing the pressure of each of these independently. Which direction are they going to go? Okay, let's take a look here. Over here, we've got 2 moles of gas, and over here we've got 1. So if we increase the pressure, we are going to move towards making more product. Here we've got 4 moles, and over here we've got 4 moles. So these guys are equal, so we're going to have no change in how our reaction is taking place. Here we have 6 moles because this guy is not going to count. He's a solid. And over here we have 0 moles because this guy is not going to count because he is a liquid. So if we put this under pressure, then this is going to go toward making more product, because 0 is obviously less than 6. So there we go. That ends our lecture for chemical equilibrium, Brown-Lemay, chapter 15. I am going to have another video that's practice problems that you can reference to. Thank you.